In our last video, we started looking at light energy. So light energy, also called radiant energy or electromagnetic radiation, right? It was one form of energy. And we said that light energy has wave-like properties. We can characterize it by its wavelength, which we defined as being the distance between two consecutive peaks or troughs. Lambda is our abbreviation. And then also by frequency. Frequency was the number of peaks that pass by a fixed point per unit time. Its abbreviation was our Greek letter nu. And we said that the two are inversely related, right? If we were to take the speed of light, which is the speed that all of our forms of electromagnetic radiation travel at, regardless of their wavelength or frequency, it's going to be equal to the wavelength multiplied by the frequency, right? As my wavelength gets bigger, right? As wavelength gets bigger, my frequency gets smaller, right? As the distance between two peaks gets larger, less of those peaks are going to pass by that fixed point. And then also as my my wavelength gets smaller, right? They're closer together. My frequency gets larger, more of them pass by. So those are inversely related. So wavelength and frequency, it doesn't really look like a very good frequency, and frequency are inversely related. We're going to add energy this time, and my relationship between energy is that it's going to be directly related to frequency. So H is going to be a constant, it's Planck's constant, and if I was to multiply that constant by my frequency, I get energy. So in this problem, E is energy. And this equation is also provided on your periodic table. H is Planck's constant, which is given. Also on the back of your periodic table, so 6.626 times 10 to the negative 34th joules times seconds. And then nu again is my frequency. So if you take your frequency, multiply it by a constant, right? So it's not changing, we get the energy. So they are directly related. As frequency goes up, my energy also goes up. So frequency and energy are directly related. So if we wanted to go back up to this little list, as we'll add energy in here, as my wavelength goes up, frequency goes down, energy goes down. As my wavelength goes down, frequency goes up, and energy goes up. We looked at our electromagnetic spectrum also in the last video, and I'm going to just copy it down here again. So we had gamma rays. Again, I did want you to know the order of this. X-rays, ultraviolet, so UV, visible, the only form that we can see, infrared, so IR, microwaves, and then radio waves. And as we went in this direction, right, we said that we had larger wavelengths, which means we have smaller frequency, which means we have less energy. As we go in this direction, we have smaller wavelengths, so we have higher frequency, so we have higher energy. So our electromagnetic spectrum. An example problem for us. Let's calculate the energy of a wave that has a wavelength of 480.3 nanometers. So I jumped in right to kind of as hard as this problem can get. I want to calculate the energy, and it gave us the wavelength. And if I go up and look at the equations we have one that has wavelength in it, we have one that has energy in it, they just happen to not be the same equation, right? The common thing between those two, the ones that I just boxed in pink, is frequency. So we can take our speed of light equation, plug in our wavelength, solve for frequency, then take that number, plug it into my second equation, and solve for energy. Alternatively, you can combine those and derive your own equation. You can do it either way. The other thing that makes it slightly more complicated is I did give us our wavelength in nanometers. You do need to use those units on your constant to make sure that you have everything's going to cancel all right. So that nanometers will have to be converted to meters. So I'm going to put all the equations in one spot with my constants. I know that my speed of light is equal to my wavelength times my frequency. I know that energy is equal to Planck's constant multiplied by frequency. Speed of light and then Planck's constant joules times seconds. Remember, joules was our SI unit for energy. My frequency is, if it's in terms of seconds, those seconds will cancel, and we'll be left with joules as our units. So everything here would be provided. The equations and the constants are on your periodic table, so you are welcome to have those on tests and quizzes. So again, you can do it two different ways. We can do it twice, like solve for wavelength and then plug it back into the second equation. If you want to rearrange them, you can. So I'm going to take this equation and I'm going to solve it for frequency. So I know that frequency is going to be equal to the speed of light divided by wavelength. And then what I can do is I can substitute that into my energy equation. So H, and then again, I'm just substituting this part in for frequency times the speed of light divided by my wavelength. And then you can just do it in one step. Either way works. I'm going to use the one I just made, this one. If you want to do it in two separate and see that you get the same answer, that's totally cool. So I know that my energy is going to be Planck's constant, 6.626 times 10 to the negative 34th joules times seconds, multiplied by the speed of light, and then my seconds will cancel. And then that's going to be divided by my wavelength. My wavelength does need to be in meters, however, to get my meters to cancel. So as a side here, I have 480.3 nanometers. We know that there is 10 to the 9th nanometers in 1 meter. So I know that I have 4.803, don't lose sig figs here when you do this, times 10 to the negative 7th meters, right? We just did this and then substituted that up in there. Units, they will cancel because we did that conversion from nanometers to meters, so meters cancel, these seconds cancel, and I'm left with joules, which is my unit of energy. Always double check. That's where you'll catch any conversions that you might have missed. So typing all of this into my calculator, which hopefully you guys will do also. When there's a lot of scientific notation, again, this is where folks that are pretty new to scientific notation and their calculators can get it goofed up. So just please be careful, which is why I want you to play along. So you find all those mistakes now before the quizzes. And I ended up with 4.136 times 10 to the negative 19th joules. which is a pretty small amount of energy, but is typical for something in the visible range. This is actually in the visible range. Significant digits, this is 4, this is 4, and this is 4, so I do have 4 in my answer. So I had said that light energy has wave-like properties, right? That's where we were defining wavelength and frequency. It turns out that it's actually more complicated than that. Light has dual behavior. So it behaves like a particle as well as a light, or as a wave. So dual behavior. So it has both wave-like and particle-like properties. And it's actually pretty complicated and kind of weird to think about. And we're not going to get into it in this class. If you were to take a physics class or a physical chemistry class, you do spend more time on the dual behavior, but I do want you to know that it has both the wave-like properties that we've been talking about, but then also particle-like properties. So we're saying maybe it has mass, that sort of thing. De Broglie, he then suggested, well, if light has particle-like and wave-like properties, then maybe so does matter. So he suggested that matter can behave in some respects like a wave also. So suggested that matter could also have wave-like properties. So if you were to take a particle, right, something that has mass, and have it move, like throw a baseball sort of thing, we're saying it could also, right, de Broglie suggested it would also have a wave-like pattern. You could define the wavelength of that particle as it moves. So we could calculate the wavelength of a particle. And we have the de Broglie wavelength equation. So this is also on your periodic table. So lambda, that's our wavelength again. And then h for Planck's constant. And then this is where it gets kind of messy, so be careful. M is going to be mass. So again, particles have mass. So calculating the wavelength of a particle, it is dependent on how much matter it's made up of. So mass is going to be part of that. And then this is where you have to watch out, V. This is not nu, this is V. So velocity. And we're just going to use speed. I get that there's a difference between speed and velocity, but we're not going to really care so much about the direction. We just care about how fast it's moving. What is its rate of movement? So in our equation here, lambda is still my wavelength. H is still Planck's constant. It's still constant. It's still on the back of your periodic table. M is going to be my mass. And then this is really important for our units to work out. The mass does need to be in kilograms. If it's not in kilograms, our units will not work. Remember, 1 joule, if we were to look at the components that make up a joule, right? It's a derived unit. It's a kilogram meter squared per second squared. So for our units to cancel, that mass does need to be in kilograms. And it's not really obvious. Usually you can just look at your units and get them to cancel. But because a joule is a derived unit, if you're not remembering this, then it's not really obvious. So that mass does have to be in kilograms. If it's not in kilograms, it needs to be converted to kilograms before you can plug it in. Or you need to convert joules to something in terms of whatever your mass is, which is going to be a lot more work. So I would just make sure your mass is in kilograms. And then V is going to be the speed at which that particle is moving. Since mass is on the bottom, right, the bigger my object, the smaller the wavelength. So something large like a car, the wavelength would be super, super tiny as it moves, which is why we don't observe it. So the bigger it is, the smaller that wavelength is going to be. The faster it's moving, right? My speed is on the bottom again. The smaller my wavelength is going to be. So let's go through an example problem. We are going to calculate the wavelength of an electron. And the mass of our electron is 9.11 times 10 to the negative 31st kilograms. If it wasn't in kilograms, we would need to convert it. And then its velocity or its speed is 5.31 times 10 to the 6th meters per second. So this one's pretty straightforward. I don't have to do any conversions because I have the correct unit, so I can just plug it into my equation. So my wavelength is going to be equal to Planck's constant. And I am going to write joules out so you can see how the units cancel. So instead of putting a joule times second, I'm going to write a kilogram multiplied by a meter squared over a second squared, and then that's multiplied by seconds. I just want to show you the units here. And then that's going to be over our mass, 9.11 times 10 to the negative 31st kilograms, multiplied by my speed, 5.31 times 10 to the 6 meters per second. So units, this seconds cancels one of those seconds, right? It's seconds squared, so seconds times seconds. Kilograms cancel kilograms. This seconds is going to cancel my other seconds. And then I have 1 meter here, so that's going to cancel one of those meters, right? Meter squared is meters times meters. That's going to leave me with meters as my units. Remember, wavelength is a length, right? Distance between two peaks. So my units do have to come out as a unit of length, and it does. Again, if you didn't convert those, if your mass wasn't in kilograms, you would need to convert it to kilograms. Otherwise, those units are not going to cancel properly. So my wavelength, grabbing my calculator here. I hope you guys will do the same and play with me. So let's type it in. Still typing. And I end up that the wavelength of my electron is 1.37 times 10 to the negative 10th meters. I have 3 significant digits in that answer. Let's do one more example where you need to do some unit conversions. So let's calculate the wavelength of a baseball. So we're going to calculate the wavelength when a 145 gram baseball is thrown at a speed of 105 miles per hour. So unit conversions, right? We're going to use our de Broglie equation. It's Planck's constant, which is joules times seconds for units. My mass, which needs to be in kilograms, it's giving to us in grams, so that's an easy conversion, right? 10 to the grams in 10 to the third grams in 1 kilogram. So we can just move our decimal place over 3. And then multiplied by my speed, which needs to be in meters per second. If we go back up and look at this last example we did, these meters and seconds canceled a second and one of my meters. So we could go back up to our equation here, this v, speed at which the particle is moving, and then we could add in meters per second. Again, your units need to cancel. We need to end up with units of length, so make sure that that happens. I am just going to convert. I've already converted my velocity, so miles per hour. And when I convert that, I get 46.9 meters per second. I want you guys to try that on your own and make sure you get that. If you're still not doing very good with dimensional analysis, you still feel you need help, please, pause the video, do that conversion, and get the 46.9 meters per second. If I was to give this problem to you on a test or a quiz, I wouldn't, convert it for you. You would have to do it on your own. So again, please practice that conversion. I know that my mass needs to be in kilograms. I can divide it by 1,000, move my decimal place over, so 145 kilograms. So now we can just plug everything in. So my wavelength is going to be 6.626 times 10 to the negative 34th. You can leave it as joules. I'm gonna double check my unit, so I'm gonna write that out. It's not cubed, it's squared. Meter squared per second squared times seconds by 145 kilograms. This is where if you forget to convert something, if you would have left your speed in miles per hour, they would not cancel. So 46.9 meters per second. And then again, just double checking units. This second cancels one of those. This is my other second. Meter cancels one of those meters, and then kilograms. I'm left with meters for my unit. So calculator. And I got 9.74 times 10 to the negative 35th meters as my answer. And remember we had said a little bit ago that as the mass of my object gets bigger, right, as it's composed of more matter, my wavelength is going to get smaller. So if I was to compare the wavelength of a baseball, which is obviously much larger than that of an electron, right, my wavelength is much smaller. So for my electron, times 10 to the negative 10th, for my baseball, times 10 to the negative 35th. We don't see that wavelength because it's just too small for us to observe.